Hello, everybody. Today we're working on Chapter 8, Intermolecular Forces of Liquids. This chapter goes hand in hand with Chapter 7, which is Intermolecular Forces of Solids, and with Chapter 9, which is all about gases. So we're going to talk about liquids, a couple of things about them that are a little bit different than solids. We're going to talk about their properties, solubility, meaning what dissolves in what, and some particulate representations of solutions, and vapor pressure. All right. So we're going to start with mixtures. And you've heard mixtures a whole bunch of times in your science classes before. The two main types are heterogeneous and homogeneous. Heterogeneous mixtures are just not evenly mixed. All right, for whatever reason, the things just aren't completely integrated together. And because of that, you have different properties in different regions of the solution. And because of that, it's really hard to do like a chemistry problem because you have to account for maybe a different concentration of chemicals in different parts. And that's not really something that we have to worry about. All of the solutions we're going to deal with in our class are considered to be homogeneous, which means they're completely evenly mixed. So you're expecting that the top of your vial has the exact same concentration of chemical as the bottom of your vial. You have the same properties all the way throughout. And we kind of make that assumption without ever saying it, but these are the things we'll be doing chemistry with. Homogeneous mixtures are solutions. Now, you can have mixtures of solids, liquids, gases, or some combinations of them. A homogeneous mixture of a metal is an alloy. That's multiple different types of metals joined together. You have a couple different types of alloys we learned about. Homogeneous mixtures of gases exist, and things like our air that we breathe is all sorts of different gases relatively evenly mixed up together. And today we're talking specifically about homogeneous liquids, which is multiple different types of liquids added together and like mixed up completely evenly. And we know they're called solutions. And we also will talk about things being dissolved in water, mainly solids that you dissolve in water, being aqueous. So something dissolved in water is aqueous, and we give it its state of matter symbol, an AQ in parentheses. Now just a bit of review. The solute you'll see written is the thing that you are dissolving, the thing that is being dissolved. For us, this could be all sorts of different things. Salts, acids, bases, other solids and liquids can sometimes dissolve as well. And these things will always be marked in a chemical reaction with their state of matter symbol as well. Solvents are the things that do the dissolving. Unless stated otherwise, it's almost always water, but there's other ones as well. There's other organic solvents. Things like ammonia, acetone, alcohol are better at dissolving certain things than water is. Water's a really good universal solvent, but it doesn't dissolve absolutely everything. It's really bad at dissolving like non-polar compounds and stuff like that. So you'd use something like acetone or maybe not alcohol, but benzene or some sort of organic solvent to help dissolve those sort of things. Now, this is something we talk about all the time, but just to give you some formal notes on molarity. Molarity is the measure of how concentrated a solution is. And I expect us to all know this already, but it doesn't hurt to talk about it again because we'll use it a lot still going forward. I would say like half the chapters from here on talk about molarity in some way. So it is abbreviated with a capital M, right? And its formula we already have, but it's the number of moles of solute divided by liters of solvent. The unit for molarity is moles per liter. And just to like check the language, if you're reading a question, if I say like a 1 molar solution, that's just telling you it has a molarity of 1 mole per liter, or a 12 molar solution is a solution with a molarity of 12 moles per liter. So if you see that language like a something molar solution, it's just telling you its molarity. All right, so just to run through an example or two, just to make sure we're up to speed with molarity stuff, we have a couple problems here. So I want to know what's the molarity of a solution of hydrochloric acid, HCl, with 4.2 moles of HCl dissolved in 500 milliliters of water. This is the kind of problem we've done a whole bunch of times already, but this is technically the chapter we're supposed to learn it, but we need it in the lab so much. So we already know how to do this, but molarity is capital M, moles per liter. So you have 4.2 moles per liters. It doesn't give me liters, it gives me milliliters. 500 milliliters. So we need to remember for sure that 1,000 milliliters makes up a liter. And because of that, I don't have 500 liters, I have 0.5 liters. Then 4.2 divided by 0.5 is the same as multiplying by 2. So you get 8.4 molarity. Not too difficult. We have another problem that's essentially the same here. How many liters of solvent would I need to create a 10-gram sample of solid HF? What I need to add to is what that should say. I need to add to a 10-gram sample of solid HF to create a 1.5 molar solution of HF. So I have a little bit more complex version here. I'm looking for liters. How many liters do I need? How many liters of solvent would I need? Okay. I know my molarity. I'll just write my formula. But I know my molarity is 1.5. Because it says 1.5 molar solution of HF. Now my moles I don't directly have, but I know I have a 10-gram sample of HF. So I'm just going to convert this to moles really quick. Grams of HF. Oh yes, don't forget mole conversions. Okay. 1 mole of HF weighs, if you go to the periodic table, it's about 20 grams. Not 26, 20. 10 divided by 20 is 0.5 moles of HF. Take that, plug it into my equation. 1.5 molar equals 0.5 moles per liter. Now I just need to solve for L. I'm going to multiply it both sides by L to get it out of the denominator there. 1.5 L equals 0.5. Divide by 0.5. L equals, divided by 1.5. L equals 0.5 divided by 1.5. 1/3. Summarize everything there. We had to go grams to moles, plugged in moles. We knew molarity, plugged in molarity, and then we're just solving for L. Multiply L up here, and then you have 1.5 times L equals 0.5. So I divided both sides by 1.5, and then got L equals 0.333. So just cleaning that up a little bit. Okay, and another thing we've already done, because we have to do this in labs all the time, is dilutions. Now, we're going to do the same math that we normally do with dilutions with our formula, M1V1 equals M2V2. A stock solution is a concentrated solution you can make a weaker diluted solution from. So that vocabulary will come up in questions quite a bit. Stock solution, meaning the thing that you're making it from, but it's generally very concentrated, so you can make a lot of weaker diluted solutions from it. This formula below can be used in a variety of different ways to find different math about dilutions. You have M1 and V1 stand for the molarity and volume of your original stock solution, and M2 and V2 are your new volume and your new molarity of your diluted solution. So all sorts of different math we can do with this. This one says, I have 1 liter of a stock 12 molar hydrochloric acid solution. What volume would I need to dilute the solution to make its new molarity 0.5? Okay. So I'm going to do M1 V1 equals M2 V2 because I'm dealing with a dilution here. Okay. Anything about my original sample will go over here on the left. Anything about my new sample will go here on the right. So I have a 1 liter of stock solution. So I'm going to plug in its molarity is 12, and I have 1 liter of it. So both of those will go on the left side. Looking for what volume would I need to dilute the solution to make its new molarity 0.5. So I want its new molarity to be 0.5, and I want to know what volume I would need to make this solution to make it 0.5 molarity. So this isn't exactly the situation we've used this formula before. Before, what we've done is we're usually looking for this number, because usually what we're doing is making a new solution. We're taking just a little bit of this, adding it to a new vial, and then filling the rest with water. But with this context, we're using the same formula, but we're not actually doing this exact problem. Okay? So all we have to do this is solve for V2, and that's saying what new volume do you want your solution to be? So I'm taking every bit, all the 1 liter of my stock solution, pouring it into like a giant container, and then I'm going to keep adding water until it's 0.5. So in this case, I already know I'm using 1 liter of my stock solution. How much total volume would I need this to be at for it to weaken to 0.5? So, according to my math, 12 is 0.5 times V2. Divide by 0.5, 24 equals V2. So if I take this solution that's normally 1 liter and add water, I would add 23 liters of water until you have a total volume of 24. Then your new concentration, because you added so much water, would be 0.5. So it's another sort of way to use this formula. And in fact, I can give you any 3 pieces of information here, and you could use it to find the last one. And all of them kind of mean a slightly different sort of thing, depending on context. But in general, you just plug in the numbers you know and solve for the missing sort of quantity there. If 50 milliliters of 1 molar NaOH, okay, so that's my M1 and V1, my initial volume and my initial molarity, is diluted with distilled water to a new volume of 2 liters. Okay, so I'm adding a bunch of water until I get to 2 liters. The concentration of the resulting solution is, and I have some options here, but we can just calculate it. All right, so my numbers here, I have M1 V1 is M2 V2. My initial molarity is 1. My volume here is 50 milliliters. And if I'm paying attention, I have milliliters here and liters here. It doesn't matter which unit I use, but I need to be consistent on both sides. So I either need to turn this into liters or turn this into milliliters. I'm just going to turn this 50 milliliters into liters because that's the one I'm more used to doing. But you could totally get the exact same answer if you just turn 2 liters into 2,000 milliliters. 50 milliliters, to turn something into liters, you just divide by 1,000. So you can probably do it in your head, but it doesn't hurt to put it in your calculator. To get 0.05. M2 is my new molarity, and the concentration is what I'm looking for. So that's what I must be solving for. My new total volume is 2 liters. So go to 2. Now I'm just going to solve for M2. So I have 0.05 on the left equals M2 times 2. Divide by 2 to get this by itself. 0.05 divided by 2 is 0.025 is my new molarity. And that was one of the answer choices. I don't think I gave you answer choices, but 0.025 is the correct answer regardless. All right. Next thing we're going to talk about is a little bit more new stuff, is solubility. Now, solubility is a really important topic. It's talking about which things dissolve inside which things. A substance solubility is a measure of how well it dissolves in a solvent, which is usually water, is what we're talking about. Ionic compounds, things like salts, are usually soluble in water. Things like just regular table salt will dissolve in water really well. There are some things that are salts that don't dissolve quite as well, but it's pretty complicated why. And we'll learn a little bit more about it a little bit later in the year with KSP stuff, but for now, just some of them dissolve, some of them don't. Metal compounds usually aren't soluble at all. Usually they won't dissolve. There are some exceptions, but for the most part. And then covalent compounds range from completely insoluble to fairly soluble depending on them. Some things are completely insoluble. Imagine like a diamond. Diamonds definitely don't dissolve in water. Or things that are kind of dissolving would be like sugar. Sugar is a covalent compound, but it dissolves a little bit in water. And we're going to talk about what makes something soluble or not, and try to predict which things should dissolve and which things wouldn't based off their chemical properties. Now, salt dissolves well in water because water molecules are attracted to the ions. Remember, salt is made of that lattice structure of sodium and chlorine ions, positive and negative charges. Water is polar, meaning it has a positive and negative end itself. The negative part of the water, the oxygen atom, is attracted to the positively charged parts of the salt, the cations. The positive ends of the water molecules, the hydrogens, are attracted to the negative ends of the anions, right? They're attracted to the anions, the negative charges in the salt. Right? So both parts of the salt are attracted to a part of water. So there's a lot of positive sort of attraction going on here. we think of this process of like a salt breaking down and disappearing into the water as dissolving. But what's really happening is just the water is pulling apart the ions because it's attracted to them. It wants to be around them. So your water molecules start to surround your salt anions and cations. And this happens though only because water is polar. Non-polar things wouldn't dissolve salts very well. Right? The polarity of the water allows it to separate it and pick apart the positive and negative ions because they like to mix together. Okay, and we have some examples here. We have some Na ions. Remember, those should be drawn smaller because they have a positive charge, meaning the nucleus is relatively stronger than the electrons and pulls the electrons in more. And we'll notice these positive ions are starting to be picked apart by water molecules. We have our water molecule here. Our oxygen is white, our hydrogens are red. This positively charged ion, you'll notice, is surrounded by the white parts, okay, of the water molecules, the oxygens. The negative ends of the water are all attracted to the positive salt. Okay? And that's the only reason it's allowed to break it apart, right? This is just as we'll kind of learn more about this, this is a favorable sort of chemical reaction. Over here on the right, I have a negative ion, and I should just fix this. Isn't a chemical reaction so much as like a physical breakdown, but regardless, okay. We just need to know it's dissolving. All right, so over here I have a negatively charged thing with the positive part of the water attracted to it. So you notice all of these positive ends are pointing towards the negative thing, and that'll be true for all of these different salts. And that's what's happening when something's dissolving. It's going from this lattice structure that was in before, and one by one, the water molecules are picking off parts of these salts because they are attracted to them. It's like a magnet. They're attracted to these ions. And now these ions, attracted to water like this, will just float around by themselves. And it picks it apart atom by atom, which is why we can no longer see it when it's dissolved. It's still solid, it's still there, but it's one atom, and you can't see one atom. So it's important to realize how water kind of breaks things apart, but also which direction the water molecules face. And hopefully that makes sense based on what we learned with polarity and stuff. All right, this is also related to why some things dissolve and some things don't. Now, oil, for example, is not dissolved by water. Right? Oil and water are not miscible, is what we're going to talk about in a bit. But basically, they don't, if you put them in the same container, they're just going to form separate layers. They're not going to choose to mix together. This container over here to the right has a layer of oil, layer of water. Even if I stirred this up as well as I could, and then gave it a couple minutes to settle, the oil would settle on top, the water would settle on the bottom. And one reason why is a little bit has to do with the density of the two solutions, but it's not only that. The water and the oil just don't like each other. They're not attracted to each other in the same way water and salt are. Okay. So oils are non-polar. So most oils have no polarity at all. They're made entirely of carbons and hydrogens, a little bit of oxygen sometimes, but mostly carbon and hydrogen. So they are non-polar. Okay. They have no positive or negative sort of charges. So they're not really attracted to water, and water's not really attracted to them. If you were a water molecule floating around in here, would you prefer to hang out with the other water molecules, which remember, the other ones are polar as well? So would you rather hang out with other polar things that have charges, or would you rather go hang out with these oil molecules which have no attraction towards you at all? And the answer is no. They would rather just sit with the other water molecules because they're attracted to them. There's a little bit of attraction using hydrogen bonding of water to other water molecules. Okay, over here, the water molecules are pulling apart these charges only because they're attracted to them. The positive and negative charge, this actually has a fancy name called the ion dipole attraction. Okay, so it's an ion being attracted to a polar thing, a dipole. So it's the ion dipole attraction. That's the reason that it's able to dissolve it, and that's all. Things will only choose to mix together if it makes sense, if they're attracted to each other. Otherwise, they'll rather just stay with their own particles. If water was to go with the oil, there would be some attraction due to London dispersion forces, because everything has London dispersion forces, but it has no dipole forces, there's no hydrogen bonds. If a water molecule stays with the other water molecules, it experiences all of that. There's just more attraction in the water section for the water molecules than there would be in the oil section. Liquid molecules will rearrange so that the positive and negative regions can attract each other. Polar molecules are attracted to other polar molecules because they all experience the dipole-dipole forces together. And nonpolar molecules are attracted to other nonpolar molecules. So, similar things attract other things of the same type. Polar molecules attract polar things, nonpolar things attract nonpolar things. The nonpolar one's a little bit more complicated because there's only London dispersion forces either way, regardless of where it is. There's some other complicated reasons why those are attracted that I'm not really going to go into because I don't know them. Yeah. Okay. Liquids that completely mix together are called miscible. And that's just a kind of a vocab word you might see in a question. Which of these liquids are miscible? It just means they mix together. So over here on the left, I have alcohol and water together. If you take those and you shake them up, you can imagine like an alcoholic drink. You don't have separate layers of alcohol and water. Of course, you wouldn't know that, but maybe your parents would. Okay. And then over here on the right, you have oil and water. And like we said, those don't mix, so they're immiscible. Immiscible, not miscible. Okay. Regardless of how much you have, when you mix them together, they're not going to mix. Miscible substances, no matter what ratio you have, they're going to mix together in some way. And then we have a couple examples here. We want to figure out which of the following pairs of substances are miscible. So which of these things do we expect to mix together? And it's a little bit tricky. And I think I made it a little bit misleading here. Let's go here. So some of these things are miscible and some of them are not. And it kind of comes down to a vocabulary thing. So we just learned H2O is definitely attracted to NaCl. Okay, but the problem is NaCl is a solid. So these things dissolve, but they're not really miscible. So I shouldn't have included this one because of that. I just kind of realized now looking at this. This is neither miscible or immiscible. This is kind of a different relationship, right? And kind of the reason why, if you go back to our definition here, miscible substances fully mix in all proportions. And we'll learn later that there's only so much salt you can add to water, right? Water can only dissolve so much salt. So this situation, let's not really even consider it because it's kind of a little bit misleading. So I should have put a different sort of liquid here that would have made it easier. So these things mix together, but I wouldn't ask you if they're miscible because it doesn't really apply. Miscible is talking about multiple liquids together. Okay. So sorry about that. Besides that, let's go to the other ones though. C2H6, C4H10. Okay. C2H6 is non-polar, and so is C4H10. And remember, I know that without looking at their structures because they're made entirely of carbon and hydrogen. I know they're non-polar. Non-polar things mixed together, these are miscible because they're both non-polar. Next, we have olive oil and water. Oil and water, as we talked about, there's not a chemical formula for oil, but I know it's non-polar, and I know water is polar. Because of that, I don't expect them to mix together. I'll call them immiscible. Immiscible. Okay, and my last one here, I'm just going to go ahead and copy, is CF4 and NH3. Okay, CF4 will be a C surrounded by 4 Fs. Because it's fully symmetric, and because there's more than 2 planes of symmetry, I know that this is non-polar. NH3, however, is bonded to 4 things as well, but one of them's a lone pair. Because of that, this one actually has a dipole moment pointing up, and it is polar. So again, I have one of each. So I'm expecting if I mix these 2 liquids, they should not mix as far as I know. So I'm going to call them immiscible as well. Okay, so that's all you're looking at. Do they have the same polarity or not? That controls whether or not they mix together. And there are exceptions, right? There are some times when a miscible solution can be made from a polar and non-polar thing, just depending on the situation. This happens a lot with intermolecular forces and stuff. We are using this as a sort of our guide. This can explain why. This is the trend or what usually should happen based off of their chemical properties. But there's all sorts of room for exceptions and stuff like that. Some of them you learn about, some of them aren't really important. Okay? So, but if I give you a question like this, you use the polarity as a guide to tell you which things should be miscible or not miscible. Okay, and our general rule of thumb for solubility boils down to one idea. Like dissolves like. Similar things dissolve other similar things. Polar things dissolve polar things because they're alike. Nonpolar things dissolve nonpolar things because they are alike. And solubility is way more complicated than this in real life. These are rules we use to kind of figure out and predict what things should mix with what other things. There's all sorts of actual math that goes into determining how soluble something is, how much of it you can dissolve. Depends on things like temperature, depends on all sorts like things like pressure and all sorts of other things. This is just our general rule. Like for example, you might know that if you have like an iced coffee or something like that, and you put like just regular solid sugar in it, that's like a terrible idea. You're going to have a bunch of crunchy stuff at the bottom of your coffee because the sugar is not going to dissolve. But if you have a hot coffee, that sugar instantly dissolves. And you have the same thing. You have sugar in water, but the temperature can affect solubility. And there's all sorts of other factors too. So don't think like this is all set in stone. These are rules to help guide us. Polar solvents dissolve other polar things or things with charges, like ionic compounds, because polar solvents are attracted to them. Nonpolar solvents dissolve nonpolar things. The reason's a bit more advanced, but feel free to use this as your rule of thumb. Now, a little bit more about ions specifically. When an ionic compound splits in water, or dissolves in water, it splits into its individual ions. That's kind of what our picture is showing. So in NaCl, when it dissolves, it's going to split into two free ions that are no longer really associated to each other anymore. They're going to be an Na and a Cl that just kind of float their own separate ways. They're no longer really bonded together at all. Right? The water dissolving it has split that ionic bond. MgCl2, okay, will split into one Mg ion, and the Mg ion has an oxidation state of 2+, so it'll have a 2+ charge, and two individual chlorine 1- ions, right? That's what our 2 here means. This one's a polyatomic ion, calcium nitrate. It'll split into one calcium because there's only one of them, and it has a 2+ charge because that's the charge calcium ions have, and then 2 nitrates. This polyatomic ion is made of multiple atoms, but this entire thing stays together, and you'll have 2 separate ones. That's why we always draw it this way. That's why we don't distribute this 2 to the N and to the O, because when this thing splits apart, it'll split into 2 NO3 ions that each go their own ways separately. Now, these ions allow the solution to conduct electricity. Ions, when they dissolved, we talked about a little bit last chapter, do conduct electricity, because now they are charges that are free to move where they want. In an ionic lattice structure, those charges are stuck in place and not able to move. So ionic solids or aqueous ions do conduct electricity. So I have 0.05 moles of NaCl, CaCl2, and MgO are each completely dissolved into separate beakers containing 100 milliliters of distilled water. Which beaker would you expect to have the greatest conductivity? Okay, so to set up my situation, I'm just going to start. I have 3 beakers, NaCl, CaCl2, MgO. And these are going to go into the beakers. I know you can't see this all. That's okay. And it doesn't really matter, but all of them have the exact same amount of water, 100 mLs. Just meaning they're all going to be equal. We're not going to have to do any math here, but it's just kind of showing you that they're all equal. Now they're all going to go in there and dissolve separately. And we're going to think which one conducts electricity the most. All right, so let's think about what they're going to break into. That's really what we're looking at. NaCl splits into an Na plus and a Cl minus. CaCl2, like we said, splits into a Ca2 plus and 2 Cl minuses. MgO splits into Mg 2 plus and O 2 minus. You're taking the same amount of all of these and splitting them into their ions, We're thinking, okay, which of these is going to conduct electricity the best? Right, and this is very similar to how strong these things are as a lattice.